In this lesson we will learn to select the proper material to use for your sample line. But why is selecting the proper tube material important in the first place? Improper tube selection may lead to failure of the analyzer system caused by adsorption of the sample in the tube material, contamination of the sample fluid, corrosion, stress, cracking, or gas permeation in the sample transport line.
Selecting the optimum process tube for use in analyzer sample transport systems requires critical consideration of process conditions. First, we need to know what are the different types of tube materials that can be used. There are two types of tube materials, metallic and non-metallic. Metallic such as welded and seamless 304 and 316 series stainless steel, Monel, Hastelloy, Inconel, Incalloy, zirconium, titanium, and even copper. Non-metallic such as Teflon, PFA, FEP, and PTFE fluoropolymer, polyethylene and Holler, ECTFE. What are the factors affecting sample line material selection? Corrosion, porosity, adsorption, surface roughness, coatings.
The first point is corrosion resistance. It is imperative when determining corrosion resistance requirement to consider failure and upset condition. Example, the creation of acids is common in stack gas applications when inadequate heating allows vapor to condense and combine with sulfur or nitrogen compounds, creating acids that can cause corrosion. The second point to consider is porosity and permeability characteristics of the material selected. Porosity is a measure of the empty spaces in a material. Permeability is the passing or permeation of a gas or vapor through a solid substance. Fluoropolymer tubes are common for many analyzer applications, particularly stack gas measurement, for all of its positive characteristics. Fluoropolymer material is porous and has a limited working pressure. Porosity and working pressure deteriorate rapidly as temperature increases. So consider using only thick wall tubing, 0.062 inch or 1.5 millimeters. If the porosity and/or pressure rating is not acceptable, then consider using electropolished silicon-coated stainless steel tube. While resistant to most chemicals, silicon coatings have limited resistance to acids, so caution should be exercised. This graph shows how the permeability of fluoropolymer increase with process temperature. The third point to consider is adsorption. First, we need to understand the difference between absorption and adsorption. Absorption is the condition in which any substance is taken by, or absorbed by, another substance, especially in solid or liquid materials. While adsorption, the substance like gas, liquid or dissolved solids only loosely adhere or stick to the surface of another substance that can be solid or liquid. The absorption phenomenon is a bulk one, where adsorption is a surface phenomenon. The absorption reaction occurs at a uniform rate, while adsorption reaction rate increase slowly till it attain equilibrium. Adsorption and desorption will cause delay in detecting changes of trace amounts of component, especially moisture and sulfur compounds, H2S, and SO2. The compounds may be caught up in the crevices and not reach the analyzer. Once the tube is saturated, the levels will equalize relative to the process, if the process composition, temperature, and pressure remain constant. Any change in composition, temperature, or pressure will cause compounds to be adsorbed/released at a different rate by the tube, creating a false spike in the analyzer readings. As a result, adsorption and desorption create inconsistent and unpredictable results. This is sometimes referred to as the memory effect. This problem can often be solved using electropolished and silicone-coated tubing instead of regular commercial-grade stainless steel. The fourth point is the surface roughness. Surface roughness contributes to adsorption and desorption problems associated with analyzer sample lines. The microphotographs illustrate one of the differences in tube material and selection. Surface roughness is only one factor to consider when specifying sample tube material. However, like other choices in sample system components, it can improve or limit the repeatable accuracy of the entire system. The final factor to consider is the coating. Inert coatings can be applied to the inner diameter of sample transport tubing, that dramatically change the sample system response time. This retains the pressure and temperature benefits of metallic tubing, and eliminates the interaction of the base metal with a specific analyte.